Okay, welcome. My name is Sam. I will be teaching you a short course in algebra and number theory for computer arithmetic. And the purpose of this course is to supplement a course organized by Yoni, Nazarathy and Paul Vrbik. I don't know, Paul, if I pronounced your name properly. And that is a course on computer programming with Julia. But it requires you to know enough number theory to get through that and be able to perform those calculations in Julia. Now, Paul has a 2-hour video available on YouTube here. So here's Paul's video on YouTube. It looks like it's about a 2-hour video introducing some number theory topics from a computational point of view. And those are on symbolic computations. So Paul defines a ring, field, Euclidean algorithm, and so on. What I'll be doing with you is going through the same topics essentially from a handwritten point of view. So I'll write on paper and pen with my document camera, and hopefully that'll give you a broad perspective on the topic, given that you may not have studied a course in algebra and number theory prior to this. Okay, so the specific topics that I'll go over in this short course will be, I'll start with the definition of a group and give a few examples of that, because it's important in the definition of a ring, which is what we need to discuss next. So once we go over the definition of a ring and a few examples of rings, we'll go on to talk about fields, give some examples. We'll talk about the division algorithm. So that's Euclid's algorithm, essentially. We'll talk about congruence between integers, so modular arithmetic, then the greatest common divisor of integers. So this is also Euclid's algorithm. Then the extended version of Euclid's algorithm. So there's a little bit more that goes on in the background of Euclid's algorithm, or that you get with very little extra cost. And that you can use to find multiplicative inverses of integers in groups modulo m. So again, this is congruences. Okay, so then we'll move on to some slightly more advanced topics, being the Chinese remainder theorem and applications, then polynomial rings, division in polynomial rings, and the greatest common divisor in polynomial rings, and finally Fermat's little theorem. Okay, so on the left here I have just a screenshot of Yoni's course, but the website is right here. I'm sure you have access to that. And so I'll be following that closely, but without the Julia. Again, this will be paper and pen calculations. And I'm going to start with the groups. So right now, before I go to pen and paper, I will just talk about a group with you. What is a group? So a group is a set G together with a binary operation. Now the simplest thing for me to write here was a star, but it could be a plus, it could be a multiplication sign, it could be a diamond. It's an abstract binary operation. And so what that means is it's an operation between two elements of that group that is closed, meaning that anytime you combine two elements in G, the result of that combination has to be an element of that set G. And it has to be well defined, meaning that there's no ambiguity in that definition, and you always obtain an element of G when you combine those numbers according to the rule of that star or asterisk. Okay, now to be a group, that binary operation has to satisfy 3 axioms of a group. First, it has to be associative, and now that just means that if I have three elements, say A, combine B, and then so I'm doing that first, and then I combine that with C. Well, that has to be the same as if I do the B and the C first, right? So I'll put a bracket around that, and B star C. So these have to be the same. The second property is that there exists a neutral element E of G, and what that means is that E combined with some element G of the set G is neutral, or it's an identity element, E is, so that I get back only G when I combine those. Okay, and it has to work the other way around too. So G combined with E also gives me G. Okay, and every element, let's say G of uppercase G, has an inverse. And what this means is that there exists an element, let's just choose another letter, H, in G such that G combined with H gives me that neutral element or identity element E, and the other way around as well, H combined with G gives me that neutral element E. Okay, and when this exists, we call H G superscript to, well, and it's often to the power of, written as the power of, -1, right? But this means the inverse of G in that group. All right, and some examples would be if you had addition. So if star is addition, then G inverse would refer to minus G. Okay, now if multiplication, then G inverse would be 1 over G. Okay, but for this to be defined, you have to have non-zero elements of that set. Okay, so next I'm going to go over these examples, but I'm going to do so with pen and paper. Okay, so I've just swapped the screens here. So with pen and paper, so we'll have integers mod m together with arithmetic. Then this one here is the Cartesian product of integers modulo 2, and that's the set of all pairs. So we have 0, 0, we have 0, 1, we have 1, 0, and we have 1, 1. Okay, so this is our set G. So put a bracket around all of that, and we should have a set bracket around this because that is a set. It contains 4 elements, and so it's finite. And we're talking about this together with addition. And so since it's modulo 2, we only have 0 and 1 in our set. Okay, so this is a nice example because it's not isomorphic to integers mod 4. It's a different group of order 4. Okay, next I'm going to talk about the real numbers together with addition, and I'm going to talk about the non-zero rational numbers together with multiplication. And then finally, group of symmetries of an equilateral triangle, which is a finite group of order 6, but it doesn't have commutativity, so it's a nice example. And then if I feel it's warranted, then we'll talk about the isomorphic group of roots of a cubic polynomial under permutation of the roots, because it also has the same structure as a group of symmetries of an equilateral triangle. Okay, so let's begin with our first example here. And so this one is integers modulo m together with addition. And let's choose, in our example, m equal to 3. So here we have g is equal to integers modulo 3. Okay, and my operation here is under addition. Now, I'll just list the set of representatives of these remainders modulo 3. So I'll just say this is equal to the set containing 0, and this is what we propose to be our neutral element E, 1 and 2. Okay, now we get, when we have 3, that refers to 0 because 3 is divisible by 3, and then 4 has a remainder of 1 modulo 3, so in other words 4 is equal to 1 plus 3 times 1, and so we put 4 is congruent to 1 modulo 3, and so in integers mod 3, the set that we propose as a group, we have 4 is equal to 1. Okay, so that's the way we treat this. In here we can put equals when we understand that that is in this set, integers mod 3. Okay, so let's go ahead and check the axioms here. So addition is associative in integers mod 3. Okay, so why is this associative? Well, whenever we have, so assume that A, B, and C belong to integers mod 3. Okay, so we're talking about one of these three elements, 0, 1, or 2. We know since... Now first, actually, if you just cover this up and just talk about those as integers, so in integers, A plus bracket B plus C is equal to brackets A plus B bracket plus C. So reducing modulo 3, we have A plus B plus C is congruent to A plus B bracket plus C mod 3. Okay, because we can write an equation like this and then focus on the least positive remainder modulo 3 by just ignoring this part of it. And so this property here gets inherited from the integers there. And so we have associativity in the set of remainders mod 3. Okay, but this extends to modulo any positive integer m. So we have associativity of this operation addition in integers mod m. Okay, now our next property is the existence of an the existence of a neutral element E. Okay, so second property, there exists E belonging to integers mod 3, and namely here E is equal to 0 in this case. Okay, now remember we need E plus any element G to be equal to G and equal to G plus E. Okay, so let's just verify this here. So if E is equal to 0, so 0 plus any element G, right? If we think of this in terms of just in terms of integers, where these two are integers, then we have this property inherited from that set, together with addition in integers. So the sum of 0 and any integer would just give us g, and it's the same the other way around. That's g plus 0. So we get 0 plus g is congruent to g modulo 3, or in fact modulo any positive integer m. And it works the other way around too, so g plus 0 is congruent to g mod 3, or modulo any integer m. Now just as an example, so e.g. 1 plus 0 is equal to 1, which is congruent to 1 modulo 3 when I remove multiples of 3 and just focus on the remainder. Okay, also 2 plus 0 is equal to 2, which is congruent to 2 modulo 3, right? And we have commutativity of addition for integers, and so we have commutativity modulo 3. Okay, so it satisfies the second property of a group, or the second axiom of a group. Okay, now let's focus on the third, which is to say that every g belonging to the set uppercase G, but in our case we're talking about integers mod 3, has an inverse, and we'll write this abstractly, g superscript minus 1. Okay, so, and that's such that g, in this case the operation being addition, g plus g inverse equals our identity e, which in this case is 0, and it's the same the other way around. Okay, now in particular, in this set, g inverse is defined as minus g. Okay, now let's verify this in integers mod 3. So let's first talk about in integers. So in integers, g plus minus g is equal to 0, right? Because those two add up to 0. And this is equal to minus g plus g. Okay, so reducing modulo 3, we have g plus minus g is congruent to 0, which is congruent to minus g plus g modulo 3. All right, so let's just talk about some examples of this, because it's very simple modulo 3. So e.g., if we have the number 2 in integers mod 3, so this could be 2, let's see, it could be 5, right, in integers, because these both have a remainder of 2 mod 3. It could be, let's see, 8 is 3 more than 5. We could even have negative numbers here that we're referring to that get reduced to be 2 modulo 3. So for example, let's see, minus 1, minus 4, etc. Right? All of these have a remainder of 2 modulo 3. All right, so these are integers such that these are congruent to 2 mod 3. All right, so they're equal to 2 in this set integers mod 3. Okay, now let's find the inverse. So 2 plus minus 2. Now minus 2, what's the remainder of minus 2 mod 3. So this is 2 plus 1, because if we add 3 to this minus 2, we have 1. But now notice 2 plus 1 is equal to 3, which is congruent to 0 modulo 3, because 3 divides into 3. Okay, so what I want to say here is that 2 corresponds to 1, and 2 and 1 both belong to integers mod 3. Okay, now it's the other way around as well works, because 1 plus 2 is equal to 3, which is congruent to 0 modulo 3. Now, so 2 has an inverse. Okay, but what about the number 1? So let's just write this here. So the inverse of 1, now this is writing this abstractly. I'll just make this look a little bit more like a 1. This is minus 1 under addition, which is 2, because if we add 3 to minus 1, we get 2. And so now this is a representative of integers mod 3, of that remainder class, integers mod 3. So the inverse of 1 is 2, and we have 1 plus 2 is equal to 3, which is congruent to 0 mod 3. Again, this is a very simple example because 3 is not very large. Okay, so we have the inverse so far of 1 is 2. The inverse of 2 is 1. What about the inverse of 0? So the inverse of 0, well, that's just 0 here, because 0 plus 0 gives 0 in this set. Okay, so that covers integers mod 3. Okay, so let's move on now and talk about this group, integers mod 2 cross integers mod 2. All right, so integers mod 2, that consists of the remainders 0 and 1, and we can see, just like integers mod 3, integers mod 2 is a group. And so the Cartesian product here, which consists of all of the pairs, so we have 0, 0, we have 0, 1, we have 1, 0, and we have 1, 1. Okay, so 4 elements. This is the Cartesian product of integers mod 2 with integers mod 2. Okay, now I want to take the operation to be addition, and I want to claim here that this is a group. So let's call this G. So G together with addition is a group. Now let's consider associativity inverse identity. Okay, so for all, let's put G1, comma G2 belonging to G. Right, now I could have just put a G belonging to G, but I think it's maybe clearer if I write it as a pair in this way. We have actually, you know what, I should put a subscript I and J, right, to talk about, see, I going from 1, 2, and 3, and J going from 1, 2, and 3. So I want to talk about associativity here. So G1, G2 plus, in brackets, G3 plus, comma G4 bracket plus G5 comma G6. Okay, and now I can see I actually need more letters, don't I? So dot 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 up to 6. dot 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 up to 6. So I want to say that this is the same as if I just move the brackets over. Plus G5, comma, G6. Okay, so in brackets here I have G1, comma, G2, and then plus G3, comma, G4. Right, so in other words, if I have 3 elements of G in order in this set, and I want to add those together without changing their order here, but moving the bracket over, I'll get the same thing. Okay, so for example, so e.g., let's just take the last 3 here. So 0, 1 plus 1, 0, and then we'll put a bracket around this first, and then say plus 1, 1. Okay, so this, well, let's perform the addition here inside. So what we have, we would get 1, 1, because 0 plus 1 is 1, 1 plus 0 is 1. So we have 1, 1 plus 1, 1, 1. Okay, now when we add these two together, we're working modulo 2. So we have 2, 2, but we reduce this mod 2 and we get 0, 0. Okay, so we can see it's closed. It's an element of this set. This is actually the neutral element of this set, which we'll soon talk about. But now we focus on, okay, if we had the brackets around these two, would we get the same thing? Right? And the answer is yes. So let's just do that. So 0, 1 plus, in brackets, 1, 0 plus 1, 1. This gives us 0, 1 plus, now if we add these two together, we have 2 for the first component and then 1 for the second component. So that would be 2, 1, but we reduce 2 modulo 2, and we have 0, 1. And so now we add these together. 0 plus 0 is 0, 1 plus 1 is 2, but that reduces to 2. And so we have 0, 0, and that's the same as what we had when we had the brackets the other way around. Okay, so we see in this example we have associativity, but we do in general for this set, which is fairly easy to demonstrate that it's inherited that property from the addition of integers. Okay, so we have associativity. So axiom 1 holds, which is associativity. Okay, now let's have a look at the second axiom here. Which is 2 exists E belonging to G such that E plus G is G, which is G plus E for all G belonging to the set G. Now in this case, E is equal to 0, 0, right? So you see I haven't written this as a pair. I could have. I would write it E1, E2, which probably makes it easier to see, but it's more to write. Okay, so now to show that this element exists, we produce it, and then we show that it holds for all of the G in the set there. Okay, but we can go through exhaustively and do that. So 0, 0 plus 0, 1 gives us 0, 1. Okay, so tick, that holds there. And it's the other way around too, because we know we can move these around. We have the commutativity property, so no problem there. Also 0, 0 plus 1, 0 gives us just 1, 0. So yes, that's true. And for the other one as well. Okay, so yes, we have an inverse given by this right here. E is 0, 0 in this set or group. Okay, now let's have a look at the third one, the third axiom. does every element have an inverse, which I'll just say inverses exist. Okay, so let's explicitly find the inverse of every element. So 0, 0 inverse is just 0, 0. The inverse of 0, 1. Well, that's just 0, 1, because if I add 0, 1 to itself, I have 0 plus 0, 0. 1 plus 1 gives 0, because we're working modulo 2. Okay, so 0, 1 is its own inverse. 1, 0, that's the same story. 1, 0 plus 1, 0 gives 0, 0. So the inverse of 1, 0 is 1, 0. And the inverse of 1, 1 is also 1, 1 in this group, because 1, 1 plus 1, 1, they would add up to 2, 2, but modulo 2, we just get 0, 0 when we do that. So 1, 1 is its own inverse. So in other words, in this set, or in this group, G inverse is equal to G. Okay, and that makes this different from, so let's just note, this is different from, or different to, integers mod 4, since in this group, integers mod 4, the inverse of 1 is equal to 3, since 1 plus 3 is 0, and 0 being the neutral element or identity element of integers mod 4 there. Okay, and 2 plus 2 is 0, so 2 is its own inverse in this case, but 1 and 3 are not their own inverse in this case. Okay, so what we say then is that, that these two, this group and this group here, do not have the same structure, the same algebraic structure, but they do have the same order, right? So same order but different structure. So we'll say that these are not isomorphic to one another. So I've put the symbol for isomorphism there, and it's often just with one horizontal line and a tilde above that. So I'll just change that. So not isomorphic to integers mod 2 cross integers mod 2. Okay, so these don't have the same algebraic structure, and we see that because this group, which is called the Ver group, has every element being its own inverse, whereas this one does not. Okay, so now that brings me probably to talk briefly about Cayley tables, right? So for a finite group, so in finite groups, multiple actually, we can write a Cayley table. Now let's do this for integers mod 4 under addition. So for that one we had 0, 1, 2, and 3, 0, 1, 2, and 3. Okay, and what we want to do is just write the binary operation of these, right, in this. So this is an example of a Cayley table, but I'll also do so for the Ver group. And so I should probably just put that over here on the left. Okay, and I'll write 0, 0, 0, 1, 1, 0, and 1, 1. I'll write this down that column as well. 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so just so we can compare this, because this is an important concept in groups, rings, and fields. Okay, so let's just take all of the sums here for this simple integers mod 4. So up here, I guess, or actually down, let's write it down the bottom. So integers mod 4 under addition here, and on this side we're looking at integers mod 2 cross integers mod 2 under addition. And these are two different groups, right? We've seen they don't have the same structure. But let's fill out this Cayley table. So 0 plus 0 is 0, 0 plus 1 is 1, and so on. We know these are neutral. We know that 0 is neutral, so we just have to copy down that top row. And the same here in the column 1 and 2 and 3, because, for example, 0 plus 3 is 0, right? Which is the same as 3 plus 0. Okay, so 1 plus 1 is 2 modulo 4, 1 plus 2 is 3 modulo 4, and 1 plus 3 is 0 modulo 4. Okay, and actually I think I want to make a double line just to distinguish here between the other lines and rows and columns there. All right, so you can see I have in this row, I have every element of this set here, and that tells me that every element here, well, actually, what does it tell me? It tells me that it's closed under addition, the operation is, and that since I have a 0 there, every element has an inverse. If I get 0 in every row and every column, which I will. Okay, so next, 2 plus 1 gives 3. 2 plus 2 is 4, but 4 is 0, modulo 4. And then I'm missing 1, so 2 plus 3 is 5, which reduces to 1 modulo 4. Okay, 3 plus 1 is 0, and we have commutativity here. So we're going to have a symmetry about this diagonal. Okay, 3 plus 3 is 6, but 6 is congruent to 2 modulo 4. Okay, so this is a complete Cayley table here for integers mod 4 under addition. Okay, now we have a 0 in every row and every column, so that's saying that every element has an inverse. And let's see. Okay, so let's do the same thing over here for the Ver group. So we know that every element is its own inverse, so that means then that 0, 0 should be down all of the diagonal elements here of this Cayley table. Okay, now let's copy down the first row there in the first row of the result. So 0, 1, 1, 0, 1, 1, and then the same thing down here because we have commutativity. And when we do have commutativity in our group, we call it an abelian group. Commutativity holds. When it holds, we call it an abelian group. So this is an abelian group, this is an abelian group. Okay, so that means that we have a symmetry about the diagonal there in the Cayley table. So 0, 1, 1, 0, 1, 1. Okay, so there's a neutral element of the group here. Identity element is 0, 0. Okay, 0, 1 plus 1, 0 is 1, 1. Okay, 0, 1 plus 1, 1 is 1, 0. So I have the same things down this second column here of the result. Okay, now 1, 0 plus 1, 1 is 0, 1. I have 0, 1 here as well. Okay, now if we renamed these letters, we can do a renaming here. So I might rename this one 0, right? So let's actually do the renaming. So rename elements of the Cartesian product here. So if I did rename them here, and I'll make a very small Cayley table so you can see. So same operation. Okay, I want to rename them in order. 0, 1, 2, and 3. 0, 1, 2, and 3. So I'm just naming this one 0 here. And I'll draw up the Cayley table for that, because I think it clarifies that these are not the same structure. Okay, so we would have 0 down the diagonal. Now this one is 1, so I'm going to put 1 there. That would be 1 there. Now let's look in here everywhere to see if we can find that 0, 1. Okay, so we have it there and there. So that would be there and there. Okay, now I want to label this one. I want to rename this the number 2. Okay, so I want to seek out where that is here. That's in the third column of the result. So that would go here as well. Okay, I have other 1 zeros in this. So we've got those. We have it here and here. Okay, so that is this spot and this spot. And then the last one that remains is the 1, 1, but we've got this along this diagonal. So we rename that 3. And here, if you compare this one to this one, you can see that these are not the same Cayley tables now, right? So we do not have in this one zeros down the diagonal. We still have the 3's down this diagonal in this, right? But now we've got a 2 here and a 0 in this spot. Okay, so we can see not the same structure as this one. So not isomorphic. Okay, because when I did this renaming, which we call a map, that map did not preserve the algebraic structure of this. Okay, so these two are not isomorphic. Okay, so these are 2 examples of finite groups of order 4, and there's a nice result that says that every finite group of order less than 6 up to isomorphism, and that means that when you rename the letters and look at isomorphic structures, all of those groups of order less than 6 must be abelian. Okay, so they're commutative. And that's rather easy to prove. But I won't do so because this is a very short course. Okay, so let's now move on to talk about the next group on my list to discuss. And that is just the real numbers under addition. Okay, so between any 2 real numbers, there's another real number. Okay, so we have associativity. So for all, let's say A, B, and C belonging to the set of real numbers, we all know that it doesn't matter which one we add first. So A plus B plus C in brackets is the same thing as A plus B in brackets plus C. And in fact, we know this so well that we don't even write the brackets, generally speaking. So we can just put A plus B plus C. And when you understand that this works, you don't have to put the brackets, okay? So we have associativity for this structure here. Now, let's talk about the inverse of an element. So this is axiom 1. Associativity holds. Okay, axiom 2. Every element there exists a neutral element of this set. And in this case, it's 0. So 0 is the identity of this algebraic structure. Okay, so 0 plus a is equal to a, which is the same as a plus 0 for all real numbers a. Okay, now the third axiom, does every element have an inverse? So let a be an element of the real numbers, and let b be equal to minus a. Then we know that a plus b is a plus, in brackets, minus a. Well, these two add up to 0, right? And it's the same the other way around. And so every a belonging to the real numbers has an inverse, namely minus a. Okay, so this is another very simple example of a group that you're already familiar with, and you would have learned this in probably grade 1 or 2, right? Just not told it was a group. Okay, now let's talk about another group in which we're not referring to addition. Okay, so rational numbers is the set of all a over b such that b is not equal to 0 and a and b are integers. Okay, now that's a description of the rational numbers, which you would already know. Now you can always assume that when you have these, that the greatest common divisor of a and b is equal to 1, because you can always reduce your fractions. Right? Furthermore, you can always assume without loss of generality that the denominator is a positive integer. So let's just make the assumptions here. We may assume W log, without loss of generality, that GCD, greatest common divisor of A and B, is equal to 1, and B is positive. Okay, we already know it should be non-zero, but we can assume that it's positive by putting all the minus sign upstairs in A. Okay, so whenever you're proving things with irrational numbers, it's a good idea to make these assumptions because it makes your job easier. And also, for example, if you're proving that the square root of 2 is not in this set, then you want to make these assumptions because later you find a contradiction to those assumptions, right? Which tells you that the square root of 2 is in fact irrational. Okay, but our task here is to consider integers, and I'll put an asterisk up here in the superscript, and we're going to consider this together with multiplication. Okay, where this asterisk means the rational numbers without, now this is set minus here, without the set containing 0. So that is non-zero rational numbers. Okay, so we're considering this set together with this. So this is multiplication. Okay, we claim that this is a group. Okay, and so what we have to do, now I'll just draw a line here and I'll write on the left-hand side. Do we have associativity? Well, yes, we do. Let's say A1 over B1 times, in brackets, A2 over B2 times A3 over B3 is equal to, now we don't often write these brackets when we're just taking a product of fractions, right? Because we don't need to, because we know we have associativity. So we can say that, of course, this is the same as A1 over B1 times A2 over B2 occurring first, and then times A3 over B3. Okay, now I've put these in the same order, left to right, right? But we do have associativity, we do have commutativity here, so we know that we can move these around as well. But this is an abelian group because we can move the order around as well, right? Which is not this property, right? So that would say A1 over B1 times A2 over B2 is the same as A2 over B2 times A1 over B1. Okay, so this is the commutative property. So this is axiom 1 that holds. It's associative. Now, next we need a neutral element or an identity element. So exists E, okay? And we know how that's defined. So let's prove it. So let E be equal to 1. Okay, in addition, you often choose 0. With multiplication, you want to choose 1 as your identity element and then prove it. Okay, so let's just prove this here. So for all A over B belonging to non-zero rationals, and I could have just put P, right? And let's do that here. P equal to this. P plus, oh no, it's times, isn't it? P times E is equal to P times 1, and so this is just A over B times 1, which is A times 1 over B, or A over B. So this is neutral, we see, which is P, and that's the same as if we had done that the other way around, right? Okay, so E equals 1 is the identity element here. Now we have one more axiom, which is to show that every element has an inverse. Yeah, I'll just put my paper over the top. Okay, so axiom 3. So for all P belonging to this set, non-zero rationals, P inverse exists such that P times P inverse gives us E, but here E is just 1. And that's the same the other way around, which we know it will be because we have commutativity. Okay, so here we know E is 1. We've already shown that. So A over B, if we have P equal to A over B, then multiplying by B over A, now we know B over A exists because we have thrown away the 0. Right? So And when we perform this product, that's AB over AB, which is equal to 1. Okay? So B over A has A not equal to 0, since A over B is not equal to 0 because we are in non-zero rationals here. Okay, so the inverse of P, now this is actually equal to 1 over P, right? So this notation here is abstract, but it coincides with what you know as P to the minus 1 in this case. This is just 1 over P, which is B over A. All right, and we know that this product always gives 1, and it does so the other way around as well. Okay, so Q asterisk together with multiplication is an abelian group. Okay, so next let's have a look at an equilateral triangle. And let's label the points, or the vertices, of this triangle, A, B, and C. Okay, now we want to look at the symmetries. So underneath this, I'll write 6 possible symmetries. Now what we could do here is we could take reflections, right, about that axis of symmetry. We've got another axis of symmetry here that we could take a reflection about, and we could take a reflection about this axis. We can also do rotations. So we have reflections and rotations. Okay, so let's just look at all of the reflections here. So if we reflected about this axis, then we would have, and I'll just abbreviate this like this, okay, then this would go to A, then we'd have B over here and C here. Okay, in our first reflection about, let's call this the y-axis, all right? Now, along our next axis, this one, we have this equilateral triangle going to, now the C stays in place and the A and the B swap. So the A goes there. Okay, and then finally, if I do that, oh, hang on, no, that's this one that I've done. Okay, now if I do this one, the B would stay in place. The B would stay in place, and I would have A and C swapping. Okay, now I want to write a non-geometric way of viewing what's happened. So here I have A, B, C going to A, C, B. So I'm just writing those in the clockwise order. In the next one I have A, B, C going to B, A, C, again in the clockwise order. Now I have A, B, C, and the third one I've done going to C, B, A. Okay, so these are the reflections. Okay, but there are more when I include rotations. So if I rotate this triangle here, so I would rotate 1 over, let's go clockwise, so I would then have C at the top. Let's say the A goes to down here, and then the B goes down here. Okay, now that's not the same as those, right? So now this one is A, B, C going to, now in this convention here, I've written the top one happening first, right? So the C, then the A, then the B. Okay, and now next, let's rotate. I guess we can rotate again, but that would be, so that would be saying, okay, well, if we rotate not just 1 over, but 2 over, then we would be taking this and rotating it 1 over. So that would have us put the B at the top, and then we'd have C down here in the bottom right, and A over here. Okay, so if I write that this way, that's B, then C, and then A. Okay, so ABC goes to BCA, and I don't see that in any of these, so that's something new. Okay, next, if we, let's see, can we rotate counterclockwise? So that would have us put A in the bottom left, B and C, so that's the same as that one. Okay, so I think the one that I'm missing here is the full rotation around, okay, which is basically the same as if I take this and I rotate it clockwise 1 unit over. So I would have A, then I would have B, and then I would have C. But this one here is do nothing, right? So that's the same as do nothing. And so I can just, I know straight away that this operation here on this triangle is my neutral element. Okay, so let's list this here. ABC goes to ABC. Okay, so I have 6 elements. I was expecting to get 6 elements of this group. So I'm going to say that G is equal to the set. Now these are just permutations of the letters A, B, C, so you can think of this in another way. Okay, so we have A, B, C, then, which is this one, right? Also this one. And let's just write these in order. A, C, B, B, A, C, C, B, A, C, A, B, and B, C, A. Okay, so this is the group of permutations of the letters A, B, C. And notice here that 3 factorial is 3 times 2 times 1, which is 6, right? So I'm happy with that because I know that there are 6 permutations of 3 letters. So that tells me I have all of them there. Okay, so this is another example of a group. So we'll say that this group, G together with asterisk, where this here is asterisk, rotations and reflections. So this is a group of order 6, but, and this is critical, this is why I'm showing you this group, it's not commutative. So it's not abelian. Because when you fill out the Cayley table for this group, you'll see that P asterisk Q is not equal to Q asterisk P in general. Right, so in other words, not for all of them, but maybe for some of those. Okay, so your next task would be to fill out a Cayley table for this. And to do that, so to work out how to fill out a Cayley table for this, you would want to label these. So we've already got E. Now you would want to label these operations maybe with Greek letters. Okay, so let's see. Now the rotations here are special because that gives me a cyclic subgroup. In other words, what I'm saying by that is that these three elements, when I combine the operation, let's call it, say, sigma, when I combine sigma to itself multiple times, so rotation clockwise once, and then rotation clockwise again, I get the next one. So I could call this sigma squared, meaning applying that twice. Okay, and this one is sigma cubed because we saw that's how we actually got this. We apply this rotation 3 times and we come back to the original ABC order there. Okay, now with these, I mean, we could just call these alpha, beta, gamma here, but there's a relationship, right, between these. So I think probably might be simplest if I just call this alpha, beta, gamma. Okay, so next what I want to do is fill out a Cayley table. And I'll just put this like this next to it so we can see what's going on. Okay, so we have E, we have sigma squared, we have alpha, beta, and gamma. Okay, we'll put these in the column on the left as well. Alpha, beta, and gamma. And I think probably I'll only fill out some of this because it would take a while. But I would encourage you to fill out the whole thing. Okay, now the first one, we know this is, the E is do absolutely no rotation, which is equivalent to rotating 3 times around. So the action of this followed by another action, the result would be the same action. For example, E combined with E is the same do nothing basically twice, so it's do nothing. Okay, E combined with a rotation 1 time is just that rotation 1 time. So for example, if I do a rotation all the way around and then I do a rotation by 1, it's the same as if I had taken this and rotated it by 1. Okay, so that gives me this, likewise sigma squared. Now if I do nothing and then do the reflection about this vertical axis here, then it would be the same as if I had just done alpha. So I have alpha and likewise have beta there and gamma there. Now the same the other way around, so this is why we distinguish in our second axiom of the group that E combined G is the same as G combine E, which is the same as G. Okay, so that's why we define it in this way, because usually we don't need this, but sometimes we do, and in this case we do. Okay, so we have sigma here, sigma squared, alpha, beta, gamma. Okay, now if we apply sigma twice, we still have the same action, which is do nothing. Okay, next, if we apply sigma and then we apply sigma squared, right? So that means rotating once, and then we take this and we rotate this one 2 times, okay? So then we're going to get back to the original. So let's do this. We have A, B, C going to C, A, B under sigma. And now if we take this one and we rotate clockwise twice, okay, so we would have C going to this bottom right position, but then we have to do that again because it's a sigma squared there. That would take us down to the bottom right. Okay, so we've got to fill out what those are. If we do B, clockwise takes it there, and then again takes us there. So that means that the B ends up there, and of course the A ends up at the top. So this is the same as the do nothing, right? So this tells us this one combined with this one is equal to E. Okay, now if we did this the other way around, so doing sigma squared first. Okay, now sigma squared, that's the triangle with B at the top. Okay, and now next we just want to do a single clockwise rotation. That takes the B to the bottom right. That takes the A up top. That takes the C 1 over to the bottom left. Okay, now that is the same as the do nothing. Okay, so in this case we do have commutativity of those two elements. So in other words, we do have sigma combined with sigma squared is sigma squared combined with sigma, which is sigma, which is E. Okay, but we know this is a cyclic subgroup there of the full group, so that's not surprising there. If we only were considering rotations, then we would have an abelian group that happens to be generated by the single element sigma there. Okay, so next, sigma squared, so that's combined with sigma squared. So that's doing, so we have A, B, C, we apply sigma squared, we get B, C, A, and then we do that again. Okay, so rotating over twice. Hang on, I've got, that should be a B there. Okay, now we want to rotate twice. That means we have the B here, rotate clockwise twice. We have the C up here, and then we have the A up here. Okay, now notice that's the same as, no, it's not. It's not the same as that one. Okay, so it's not the do nothing map. It should be the same as, actually I still want my arrow there. Okay, so it's the same as sigma one time. Okay, because sigma one time sends ABC to CAB. Okay, so we can now fill out in our Cayley table that this is sigma with a 1 superscript there, but we'll leave that out. Okay, now there are several more, so I'm just going to focus on one that's not a commutative, an example of a non-commutative combination here. So for example, let's just choose sigma alpha. Okay, now the way I've defined this, and it's probably not the convention there, but I've defined it as if I do this first, but I think it's actually I do the other one first. I'm going to stick to the way I've defined this in my Cayley table. So if I first did sigma followed by alpha, which is a reflection about that vertical axis, then I would be sending A, B, C. I would be sending that to C, B, A. Okay, now let's look for what C, B, A is. That's gamma. Okay, so I should be putting now gamma here. Okay, now I want to focus on this box, right, because I suspect that it's not going to be the same thing. Right, because I told you here this is not commutative, so I don't expect a perfect symmetry about that diagonal there. Okay, so let's do this the other way around. So alpha first and then sigma. Okay, so if I did alpha first, then I would be sending A, BC to A, CB, but now I want to rotate this, so that means I put the B up at the top, and next I have the A down here and the C there. Okay, now I look for what the original triangle, which one sends the original triangle to BAC. Okay, so where is BAC here? So that's beta. Okay, so I here have beta. So then we see that sigma combine alpha gives gamma, but that's not the same as alpha combine with sigma, which gives us beta. Okay, so not abelian. It is a finite group, but that group is not abelian. Okay, so I mentioned earlier that, and I'm not going to fill the rest of this out, but I mentioned earlier that there's a symmetry between the roots of a cubic. So I'll just talk about that. So if you have something like ax cubed plus bx squared plus cx plus d equals 0, okay, so we know that because this has degree 3, that we have, say, a root or roots phi, phi dash, and phi double dash. So the algebraic conjugates of phi. Now, if you perform, so the rules, for example, so we have E saying do nothing, right? Send phi to, phi to phi, send phi dash to phi dash, and send phi double dash to phi double dash. That would be one of our operations in the proposed group of roots of this cubic. All right. Now we could do some other rearrangement or permutation of the roots. For example, we could do a cyclic permutation of the roots, and let's just call this one sigma, where phi goes to phi dash, phi goes to phi double dash, and phi goes to phi. Okay, so that one would be the same as what we have here. It has the same effect, basically, right? We have a permutation of the roots. Now, when you permute the roots of a polynomial, it has no effect on the polynomial, right? You can permute the roots and you have the same polynomial, because this polynomial here, let's call this f of x, right? A permutation of the roots would do nothing to the polynomial, so we can have an alternate representation here as x minus phi times x minus phi dash times x minus phi double dash. Okay, so you see that if we just permute the roots and multiply it out, we're going to have the same polynomial. Okay, so my claim to you here is that there is an isomorphism between the operations of permuting those roots and the operations of the symmetry of that equilateral triangle, right? So in algebra, this is a fairly important group, and it's a non-abelian group, right? This is called the Galois group. Which is a group of permutations. Okay?